So I think it's 2:21, so I think we can start. German punctuality. My name is Andrea Jaime, I work for OHB System. I'm actually not a quantum technologies expert, but I'm really happy that this room is actually pretty full. It's very big, but it's many of you here. And why am I here if I am not a quantum expert? So actually, I work in business development, and the quantum technologies in space, we see it's really a trend that it's already happening, and it's gonna continue to grow. So as a business developer, I was told, hey, Andrea, we need to look into this future trend. What is happening with quantum technologies? What is this all about? So at OHB, we actually created the Quantum Technologies Working Group, and I am coordinating with my colleagues there, looking into which are these trends on quantum technologies. So actually, I'm not sure how many of you are really experts. I hope not so many, otherwise I'm in trouble. But I have here my experts with me, so I'm covered. But just to give you a brief introduction to what is quantum technologies in space, just 2 slides. Because I believe this is the first year that this topic is even addressed at the IAC. It was never been put in a technical session or in a panel. So let's dig into this. And actually today is a very full day. We already had a special session on quantum technologies, and there is even another special session this afternoon. So what is actually quantum technologies in space? So we have seen a big revolution. Some people say, is this the second revolution, the second quantum revolution? One of the big pushes for us in the space industry was the announcement of the Quantum Manifesto 2 years ago by the European Commission. We have seen also the first QKD demo satellite launched by China, and there is a big pressure being done. So we certainly have to all jump in and see where we need to act right now. Because indeed the customers that we know have big ambitions, and we're sure that there will be the next big missions coming pretty soon. So what or which are the applications or why quantum in space? So just in one slide, very briefly, some of the things we address that has direct applications in space is quantum distribution, which has direct application for communication, secure communication, cybersecurity, defense, of course, if we are talking about security, but also cold atom sensors to understand better our planet, to understand better, to answer some of the scientific questions that are out there, inertial navigation, of course, and going into navigation, also atomic clocks. Another application that we can use in space for GNSS, Galileo, GPS, GLONASS, Beidou, for network and mobile cell handover, and of course, science, which is very deep into our space community. So, more or less, do you have an idea what is quantum technology in space right now? And I now go back to my panel, which I have three very distinguished panelists, which are covering different areas. Actually, they are all coming from Europe. So if later anybody not from Europe is in the audience and have questions or would like to contribute to the discussions, we're here to establish this dialogue between all of us and understand better what is this topic all about. So I have here to my left, Harald Hauschild, which is the program manager of the ESA Skylab program at the European Space Agency. Next to him, we have Hans-Jörg Diethuis, which is executive member for space research and technology at DLR, the German Aerospace Center, and Christoph Marquardt at the very end here on the left, which is a group leader for Quantum Information Processing Group at the Max Planck Institute of Light. So welcome everybody. A big hand of applause to them. Okay, since we're in Germany, I told my panelists that I was going to give direct questions because we want also direct answers, right? We don't want to be wandering around and not finding solutions or answers to our questions. So I mentioned already the 3 applications that we will have in space. But for you, on your opinion and based on your expertise, which type of quantum technologies actually do you see the most promising, the ones that will really change space in the next, let's say, 20 years? You all have microphones, so.
Okay, I start with that. Thanks for Andrea for the nice introduction and the invite. And actually, you covered it all already in one slide. That was very good. I think most promising, we have two distinguished areas in quantum technology. One is the sensor techniques, and one is key distribution, and both of them are going to be very important in different fields, and you covered them in your presentation already. I think especially for Earth observation, gravitational measurements are becoming more and more important to cover effects from climate change, to see how, for example, ice melting is happening and can be detected via small changes in the gravitational field of the Earth, and this can be done by this kind of sensors. And the other big area, I think, is the development for atomic clocks, optical atomic clocks, which will improve not only, but also the navigation systems like Galileo or the next generations of Galileo. And then on top, we have the security measures, and we can use the quantum phenomena for key distribution things to at least be sure that the key that has been transmitted via light is not be listened in. And I would stop here and listen carefully to what my colleagues say to that.
I think we have two major fields where we can expect real business out of space activities. This is, first of all, communication is well known, and the other field is navigation in the future. Presently, we have more than 160 GNSS satellites in orbit worldwide, and they all carry, so to say, quantum technology. Each of the atomic clocks is a quantum sensor, inertial sensor. So these navigation systems are based on the precision of these clocks. Maybe what not a lot of people know is that it's not just only a navigation system. Because of the precision of the clocks, the GPS, and in the future all these GNSS systems will become international time standard systems. So there's a completely different utilization of the GNSS satellites. So many processors on Earth rely on this unique clock system, which gives us something like a world time standard, and this has to be taken into account. So I think this field's great business and is depending on precision for the future and robustness. And this has to be improved, and that's why we are so interested in what you said, inertial sensing, is measuring time, accelerations, precision, depending on the acceleration, and distances. And the other thing, as you mentioned, is of course communication. Whatever we do in communication in the future must be more safe. I'm not a believer in only small satellite systems. For communication, we need large satellites in the future as well, geostationary satellites for safe communication between governmental organizations, and this must be based on quantum key distribution in the future. So whenever we talk about navigation and communication, quantum technology will be the key technology in the future. And if we talk about the future, we talk about the next 10, 15 years when it will start. So we have to start now. We did a lot during the last 10 years. I'm now working with this quantum technology for the last 14 years. And so I think there's a lot of development there, and we should go on in the future.
Yes, I only can second those views that the other two have said. Now, on a scientific perspective, of course, a scientific impact always will be there on all those different topics that have been mentioned. And that will be a tremendous scientific impact also regarding the fact that space technology always has been a driver for miniaturization, for really making high tech in all different fields. And also scientifically, of course, all those, and that's a nice connection, all those things that has been mentioned that have a real life impact and urgency, so to say, also will help to have a scientific impact in the possibilities that you can do for fundamental research. So this is a very nice situation where you can team up and profit on each side, both for the scientific impact and for the, so to say, real life impact that has been mentioned. And there I also would agree that especially in concerning urgency, for example, quantum communication, securing our communication, securing infrastructure, critical infrastructure, probably is the most urgent, important one, but also then navigation systems and so on.
Yeah, thank you. I think there is a consensus here that it's clear the things that we need to focus. So which are the real challenges that we're going to face right now and in the next 10, 15 years in these areas that you have said? Is actually bringing the TRLs higher, it's bridging the gap between academia and industry. Are there other challenges that we need to face first thing, so that we all know what we have to work, especially from space agencies' point of view, but also from the scientific point of view? What we need to work on?
So me again starting, okay. I think one of the main challenges is not on the technology field, it's also on the cooperation. As you said, we need all players working together, and basically we have them all here on the panel. We need industry, we need the scientists, we need the big research organizations and the national and international agencies to come together and make it happen. There was a nice phrase in the last panel saying that unfortunately money has no quantum state, so we cannot use it everywhere at the same time. It has to be dedicated, and we have to carefully select which kind of areas. From the examples that we had, we know that the high complexity for atom interferometry, for example, makes it very, very complicated to bring them into orbit and show the real advantage, as Mr. Marquardt said, for the daily life. We really need to show that this is working in reality. The same is true for quantum key distribution, where we have already industry stepping forward for some activities. We recently had two contracts on that on the ESA side, where we even were surprised of that this is happening so fast. But there's more to come, also room for agencies and the cooperation, maybe with one of the big players as well, with the European Commission, looking into quantum networks as well. So that is a bit the challenges that we have in front of us.
I think when you asked about the TRL level. TRL levels are really high. We have flight hardware for nearly all this technology. Chinese launched an experiment just 2 years ago, doing a quantum key distribution experiment, which made a record of 1,200 kilometers in free communication. NASA launched called Atom Lab into space on space station and doing experiments since summer, proving that it's easy to produce now in space. Bose-Einstein condensates, we fly atom interferometers, a lot of stuff is already flying, so this is not a problem. The problem I see is that this technology is on lab level so far. We can build this, but there are no instruments on a free market. So the question is, where's the industry doing that? To be honest, there is not less in Europe so far, although the European institutions and science institutions are leading in the world. And the problem is to transfer this technology in short time into industrial processes to manufacture instruments and so on. And this has to be solved. And I like to repeat myself many times maybe, but I think the lessons we can learn is that it's not easy to produce just disruptive technology and we make it all time. The same time, this requirements from a society has the consequence that also have to be invented disruptive tools for funding industry to come up with instruments. And this is not if we release programs where industry has to take over the roughly 50% of the costs. So we have to think about different ways of funding and doing integrated research together with our research institutions to make us fast, because others do it. In Europe we have this problem, but there are activities all over the world. I think we have to be fast, and this is only possible if we team up between industry and science institutions.
Yes, so I think I would answer that kind of twofold. One is about the funding situations and what has happened, what can happen. I think it already has happened quite a lot also in Europe, and especially also DLR and ESA have done quite a lot into that direction, some of that actually is also not so visible, but very important, that has been done in the past. So, of course, this is something that is very important and will help that. But the other thing is, from our experience, I mean, I come from fundamental science. Max Planck institutes are fundamental science institutes. And that is where most of the people come from that deal with quantum technology now. And if you want to develop something, as we said, that can really work in everyday's life and really be applicable everywhere, then you have to go out of your fundamental science research lab and really team up with the right people. That means you have to team up with applied institutes, you really have to team up with industry, and that's not easy. So what we learned is, I mean, this is of course something that you learn when doing it, that's a clash of culture. And that is something that one has to be aware of. But this is something that is very important, because if you do these things, this is nothing that you can just give away, that you say, okay, we have made the fundamental notions of that, so please, engineers, do this now. This will not work. This will not work in this context. In some contexts, it's really dangerous. For example, in security context, quantum key distribution. And what we notice is that this is an area where you always speak of this valley of death, and this is especially complicated here, because you have the fundamental scientists coming from the quantum science fields. They know a lot about this quantum science. They don't know much about all those nasty boundary conditions that you will have in real-life situations. So you have to team up with industry and with applied institutes, but then maybe those that evaluate you as a fundamental researcher will say, why don't you publish that? Because you can't publish that. So you really have to stretch to do both. And this is that we really should think about how to bridge this valley of death between fundamental science and really kind of industry to help everyone to get this to the market rather soon.
Yeah, that's actually a great topic, because in industry we also feel sometimes how we're going to pick up what is already currently on the labs and actually make a business out of it. It's not easy to see where the return on investment is coming. So actually, building up on what you just said, Christoph, which are, in your experiences, do you have already in place some programs or projects that you have found out very useful to bridge this gap, that you have already worked with industry, that actually is a good lessons learned that we can share here maybe with our audiences, or in the space agencies or in the research institutes? Is there already something that actually worked and we should continue working forward, or not yet and we have to still invent it?
I think we have great programs and ambitious goals. And indeed, we will spend much more money into quantum technology in the future. We had spent a lot of money in the past, but there will be much more in the future. And if you would ask me, my dreams would be that we spend a lot of more money into this field. But of course, we also need support. When we do a lot of things we have to do as well. But on the other side, we have to pump in more money into this. And I would be happy if the space programs will have also contents for space technologies for the future. This must be taken into consideration. Why is not so far? Because I think a lot of people haven't understood what is the potential of quantum technology. I mean, in some way, we talk about a field 10 years ago was a little bit esoteric. And 20 years or 30 years ago, we have spoken about technologies we have to do within thought experiments in textbooks. So I remember the time when we've had lectures on one atom lasers, and this no one could we could talk about, but no one had any idea that we can realize a one atom laser one day. We can, and we talked about Bose-Einstein condensates, but it had been produced the first time in the 90s. So, and all this is now coming up and comes into the into mind of people. But many people in our countries have definitely no idea what quantum technology really can afford.
Yeah, actually, just quickly from the audience, who of you felt scared the first time that you heard about quantum? Nobody? Wow, you're really confident people. I was a bit scared, like, okay, what is quantum technologies? How we can actually utilize quantum technologies in space? Okay, then you are taking up the challenge to bring quantum to space. I take it up on you.
So what I can say, I mean, when we try to deal with the situation, because I mean, what we see is then when we team up with industry, and this is happening right now, and I think this is, as you said, this is something that changed over the last 5 years, maybe up to 7 years or so, that suddenly industry gets interested, applied people gets interested. There's even something like an end customer coming up. And then, of course, suddenly you have to talk to industry, you have to talk to different groups, and then you spend your first half a year to define the language, which is normal if you have this kind of interdisciplinary approach. What the science community also thinks can help is that we do something like summer schools, we do something like teaching programs for industry, for example, where you can have some knowledge about how to deal with quantum technology, but also develop some quantum context in engineering studies, so that you have all this context from the beginning. This also would be something that would help in the future.
If I may to attend to that as well, I'm scared every day, but more about the speed that is going on, like Christoph said. Many things have evolved over the years, and they are now very mature, starting from the laser terminals that you need for this kind of applications, but also the quantum sources. Everything has been demonstrated already over the last decades, and now we have to think about the application behind it. And that is the most challenging part, as Christoph said. Talking about the same language is really difficult. And we have 2 projects starting on QKD in ESA, where actually we have a big consortium of scientists, industry, people, different areas. Security area is important, especially for this kind of application. Optical is very important. The transmission through the atmosphere. So there are many, many aspects that need to be looked at in order not to demonstrate something, which is very, very important, but also to make it happening in the frame of today's life, into real applications. And finding the customers and also talking their language is yet another challenge for all of us. So I think this is now the very exciting moment that everything comes together, and we need to screw it together somehow. But we need, as Mr. Dito said, the support of everyone, and also on the politician side. We see activities ongoing in Germany. It was on your slide, with a 650 million program looking for the technology itself. We have in European Commission a big quantum flagship program, and at least the people sitting around here interested in space need to manage to get part of that money into the space programs. That will help.
Actually, now that you mentioned these programs and the involvement of the politicians, indeed we have seen there was the launch of the quantum flagship by the European Commission, but unfortunately in the first call, none of the space projects that were submitted were actually selected. So how can we actually convince the community out there, the politicians, even those who are the ones selecting the next big projects, that actually space is also a great part on the quantum technologies arena?
But I mean, one has to say quantum technology is part of our daily life up to now. I mean, we have many technology in space based on quantum technology. Each of these clocks on GNSS satellites is a quantum sensor, so to say. And so it's not new, but it's not understood that we have to do a lot for the future, for more research to do it. That's maybe the problem. But we have a lot of technology already there, and we like to do it better in the future and have to do it better. The potential is immense. So we can give an example. If you fly over the Atlantic, each of the planes has fiber gyros on board, and this fiber gyros brings you over the Atlantic without a GPS system, and the error you have is roughly maybe 5 kilometers, 10 kilometers, like that. Okay, this is not enough to land an aircraft on an airport. Nevertheless, it's relatively nice. You can fly this. Imagine you would do it not with a fiber gyro, you would do it with an atom interferometer. You can win 10 orders of magnitude in accuracy in theory. This is the potential we have. This is accuracy. And as far as if we rely today on a clock system in space, on GPS, which gives us roughly a microsecond. This is okay for daily life, but not for all the applications we would like to have. So in the future, we have to go up by orders of magnitude better with our clocks, and that's possible. And this needs that we transfer these time signals, not with microwaves. This is much too imprecise. So we need optical systems, optical communication system between Earth and satellites to do this more accurate. It's not enough to develop clocks. At the same time, we have to develop the technologies to transfer the signals and so on. There is a huge potential for the future, and we should use that. This is precision and accuracy.
Yeah, maybe to the Flagship Contest, that's a good example, because there, what is behind that is that you really had to put in something that would show something successful as an application within 3 years. Now, 3 years, when you look into space, this is not very much. And so this is a general problem, of course, of space, which probably everyone knows here, that if you want to convince politicians, you have to convince the long-term strategic vision, because you won't have very short-term payback of those things for most of the cases. And I think this is also, in this situation, when this is not specially dealt for, this, of course, needs some extra effort to convince people.
So we might need to highlight also which are the real benefits of improving all those technologies, I guess, right? Okay, so maybe I open the floor also to the audience, since you are so great, also experts on quantum. Any questions? Everybody's an expert? You told me you were experts, but I'm sure you have questions. There you go. We have one question. Don't be shy. We're here at the IAC to actually have the experts ask questions to them and have a dialogue. So we're here all part of the space family, so don't be shy.
Hello, thank you very much for this plenary. I've had a bit to do with quantum mechanics and especially with superconductivity and quantum bits on the base of superconductivity. I'm a bit skeptic about the possibility to do this on the space stations, because I know these are very bulk technologies. What I saw minimally, one should have very low temperatures, very good vacuum. Does it worth it at all in terms of payload? Thank you.
Maybe I can say something, because based on the Josephson effect, which you mentioned for the cryogenic applications, and Josephson effect is the application. Of course, you need low temperatures. This has been done in space. You need huge tanks with liquid helium to cool down. A famous example is Gravity Probe mission made by NASA. And these are science missions, of course. But what we are talking about, quantum technology, which is based on quantum optics, is completely different. There you need you need a completely different form of cooling. We do it with laser cooling and evaporation cooling and things like that. You need light and microwaves to do it, so you can do it in normal temperature environment. The only thing you need is robust mechanics and things like that. But this is all there so far. We can fly these clocks in space, and I think there's a lot of technology developed for quantum optics. This is important. It's not based on Josephson effects. Yeah.
And I think that's a good remark, because that's a good example, because if one wants to tackle those problems, that's a challenge, but you can take it from both sides. So, I mean, there are projects now that also deal with how to miniaturize all those fridges to really make them space-proof, for example, for superconducting photon detectors and so on. But there's also thoughts about, okay, can we do something else to really achieve that? Maybe we can cope with higher temperatures, you know, going from 2 Kelvin to 5 Kelvin, making it a bit easier. And I think it's this iterative approach that is really winning. And again, there, different teams have to speak a lot with each other to make this a success.
Any more questions?
Well, I actually have a question about AI application in quantum technology field. What kind of role AI play a role in quantum technology field?
Maybe in the future in quantum computing, but this is future. What we are talking about are senses. We're talking about communication. You're talking about computing capabilities, and this could be quantum computing, but this is a completely different field. It's coming up, I feel so, but presently it's a big step to bring into AI, maybe in the future.
Thank you.
So maybe I can add what is happening right now. Of course, if you think about, okay, does that make to combine it with quantum technologies in space or so on, right? One has to be a bit cautious right now. What is happening, however, now is that people try to put in deep learning systems, artificial intelligence like machine learning systems into the generation of new quantum computing algorithms and so on, so that kind of the artificial intelligence learns how to program, how to invent new quantum algorithms, new quantum machines. So indirectly, it might play a role.
Thank you.
I would like to extend that also for applications like optical networks. If we go and deploy them in space together with terrestrial, we might need these kind of applications as well, going perhaps in the future into, I don't know, quantum networks or whatever it is will be called.
But that was a good question. Any other question now? Okay.
Hi. Maybe a naive question. When you mentioned GPS or Galileo or anyway GNSS signals broadcast by photons, by laser beams, I suppose. I don't visualize how you materialize that, because I understand very well point-to-point communications, but a GNSS receiver needs to receive some sort of broad range broadcast. So it's certainly a silly question, but I'd like to have your answer. Thank you.
But these are photons as well.
Yeah, but
different wavelengths and frequency. Of course, we have the microwave links from satellites down to Earth. That's what we need in the future as well. Otherwise, you cannot make a point-to-point connection between your mobile and a satellite. It would be a bit too complicated. But what we need connections from Earth to the satellites to synchronize the clocks, to bring up the time signal, and therefore you need higher accuracy. So it's therefore, we need the optical communications. That's what I like to say, of course.
It's the uplink, not the down.
It's the up and down link, yeah. But with stations on Earth to synchronize time signals, we need it also from satellite to satellite. We could stabilize the signal, for example, if we wouldn't have clocks on each satellite. We could store the time signal in rings in the orbit, and I think this is the future.
Hello? Oh, okay. My name is Barbara Weinhold, and I would like to ask about the radiation aspects of all these quantum experiments, because all these quantum experiments require producing highly isolated states. So how you manage, or it's not an issue, the disturbance from the radiation?
So as I understand, okay, so the quantum states are fragile, usually, I agree. So now you have to distinguish between how you encode them. For example, in the communication part, you would encode them in wavelengths that are not susceptible to, for example, thermal background radiation, right? So you usually go from microwaves to infrared or optical wavelengths. And then they have the advantage that, you know, electromagnetic waves don't like to interact with other electromagnetic waves. So that's quite nice. So there's not much decoherence. Of course, there's decoherence through loss and so on, and one has to be careful there. I completely agree. But if you look at the numbers, if you do it the right way, it still works. With other systems, if you go to atomic systems and so on, that's of course true. You really have to make a lot of effort to isolate them from the environment. And this is really what makes the challenge of making these missions. But it has been shown now in various missions, for example, MAIOS or the other missions, that indeed that this is even possible in space. Of course, to make this more applicable in all sorts of satellites, there still is a lot of things to be done.
Yeah, I just can agree to what Christoph said. It has been done in a couple of missions already to isolate them, and there are means, and I mean also other elements on the satellite are very sensitive to radiation, so we have means to do so, but it increases the complexity, and this makes the whole missions very complex and very expensive. That is the main challenge, I would say. Not so much technically, but getting it all together and getting it financed.
In fact, I would say that this is one of the reasons why we need to bring together all the experts that they are working in the lab with the space experts who understand the space environment and what needs to specify, let's say, the current existing technologies. Okay, great, thank you for the questions. Maybe we have more questions later. There will be more time. I'm just gonna ask one more for you guys and then open again to the floor. So this one for Harald, for example. We have seen you mention the Skylab program at the European Space Agency. So it's very clear that QKD is the first technology that you have embraced in the ESA program. But are we going to see other quantum technologies, let's say, also supported at the next ministerial? What do you think will be coming?
Multiple questions in one. First of all, the Skylab program is not only quantum communication, it is optical communication as such. Exactly, and we have included there the quantum part initially as an area where we wanted to see the scientists being active, giving them also more chances to bring in their proposals. And then we were overwhelmed already by the first application, which is a very positive thing, especially in the program where I'm working on. And this encouraged us also because we see that this is possible, that industry and scientists are working together, which is, as I said, one of the challenges. We will use in that area the ministerial conference to propose also other missions, but still in the frame of quantum cryptography, quantum key distribution. Perhaps we need to look a bit, like Mr. Ditto said, into geo applications there, and look there. That has its own challenges. The signals are very, very low, and the receivers are still to be developed. The Chinese have done a lot and shown that it's feasible, but I think we still have, if you go for real applications, still some challenges ahead. That is something we want to address at the next ministerial conference. And in the other fields, we will continue with the programs for quantum technologies in general, together with the national partners. So that would be my
answer. And indeed, this is what we see in ESA. Okay, I'm happy to hear that we will see more quantum-related activities happening in the next years. What about the DLR?
We have plans.
You already have,
we concentrate on developing quantum sensors. We did a lot in the past, I said, atom lasers, but also optical clocks. That's the keyword, I guess, in the future. But not only on that, also on accelerometers. And I like to touch a field we haven't touched so far, is satellite geodesy. Presently, we base it on radiometers based on 2 satellites, and we like to do it on one and make the accuracy much higher. And this can be done, of course, with quantum technology. So I think it's quantum technology, it's quantum sensing, and then the third field is, of course, quantum key distribution. We have some experiments running now, and we prepare an experiment together with him on in space with our Communication and Navigation Institute with small satellites now based on that. But we did it in the past on aircraft with aircrafts where we transmitted high rates of down to Earth and then demonstrated quantum key technology also from aircrafts down to Earth. It's not the record so far, but I think what we have to think about is in the future how we can improve the technology the Chinese experiment demonstrated by using maybe technologies like quantum memories and things like that, so that we can really base all communication system on quantum key distribution.
Would you need more push from industry to go to you to tell you, hey, we need more funding for us to be part of this quantum technologies area? Or do you think it's actually the scientific community who still needs to go to you pushing for more funding, and then the scientific community linking with industry? So what would you like to see?
I start with that. Both. Actually, we need both. We need both players, but we strongly believe that the application will make the challenge now. Now that we have done a lot of fundamental research, it's perhaps time to look in real applications. And I think here the industry is in the forefront to show that this actually can work and that the investment is worth it. Of course, fundamental physics needs to be supported anyhow, so that needs to continue or being increased as well. But the application part is now the one that needs to be grown, and there's clearly industry in the lead.
Yeah, I think there's a lot of need to develop, and usually these demands come from many other authorities. We didn't mention military authorities, of course. I mean, there's a lot of need to develop these kind of technologies. So I think the civil sector is also influenced more and more by that. The demand is there. What is missing so far is engagement. That's what I see from industry. On the other side, I also recognize that I wouldn't go into this field as industry if there is no funding. And this is what I said before. We have to find a way how we can support disruptive technology fields. And quantum technology is one of the fields. They had a very, very exponential development. It's always developing exponentially. But in this case, we are in a very steep gradient, and it's going up. And what had been in labs 10 years before is now in principle adapted and applied in many fields. So I think there's a lot of application. Space is ideal because atoms don't fall. We have weightlessness, so the quantum sensor always runs better in space than on Earth. Nevertheless, and that's what I criticize with this title, is not how will quantum technologies change the future of space, but we should say how quantum technology in space will change our future.
So what I can tell on the experience, what we had with our endeavors so far, is that, of course, the fundamental science you need for triggering the applications and implementing the applications, but also on the other way around. If you have the applications and you team up with industry, with applied institutes, you trigger new questions in fundamental science. We had this often when we really then saw, in a real-world problem, this is now completely different. We have to look at this from a different perspective. And then you sit down again and you're at the fundamental problem again. So I think both can profit a lot, and also the pure fundamental science questions can profit a lot from the technology that is developed in the more applied fields here. So I think this is a very nice combination.
I'd like to add I forgot one remark. All Bureau of Standards worldwide agreed recently on setting the unit system, the so-called MKZ system, the unit system on quantum effects. And what might be not interesting for many people is a big market, because in the future, all calibration units for whatever you can measure will be based on quantum effects. There's a lot of advantage, but this needs instrument development. And I think this is one of the strongest application field on Earth in the future. And for example, the Bureau of Standards in Germany, PTB, is working strongly on this and is developing programs how to bring it into industrial manufacturing.
Just actually out of curiosity, how many people in the audience is working or comes from industry? Okay, good. And how many from the scientific community? Good, so I could see it's more or less half and half. So we have seen that actually we need to talk with each other. So half and half here, you have a lot of talk to do today, later or tomorrow in the networking sessions. So I again open the floor to the audience. There were a couple more questions around.
Yeah, I just want to ask one quick question about the application side. We are looking for everything in the space aspects. Is there any non-space aspects? For example, oceanography. They need ocean mapping and everything. Maybe this quantum technology may be useful for the other non-space application. So maybe I can get a few more words about this aspect also.
It's certainly good for business. We need to look where are other applications. So I'm also interested in this question.
Yeah, so generally, of course, I mean, all this Earth observation and so on, I think this has been mentioned shortly. If you have the opportunity to have these very precise clocks, to have atomic interferometry, to really do geodesic sensing and so on, this will all profit either directly in some cases or indirectly, because you know more about the Earth and the behavior of all those systems that you really want to look at. And generally, I'm sure that once you have those systems and you have them operating and people know, okay, I can have really that precision, there will be additional applications that come up that we don't know yet, as always happened in the past.
Any other question? There were also a couple of questions around here before. Not anymore? There is one here.
My question is also related to this exact title. I think materials engineering has always driven space technology. So do you think that in the future there's a role to play for quantum simulation in the Feynman sense to improve space technology?
I didn't understand really the question. You mean, I mean, we cannot solve all questions with quantum technology. We will not bring up satellites by quantum technology.
So maybe, I don't know, maybe I might have understood the question. If you want to indirectly use quantum technology, for example, quantum computer and quantum simulation, to solve more or less classical problems in space, for example, producing new materials and so on. Yes, absolutely yes. This can happen, right? I mean, this is, so when one speaks about that, that is not only kind of directly applying quantum technology in the satellite, but also this will help you to build better satellites or better spacecraft indirectly. Absolutely yes.
There was another question somewhere here before.
Hello, my name is Janusz Sokołow. When you say about quantum telecommunication, you said about increasing the safety of that. But what about using entanglement states of quantum of quarks and make communication with, for example, Mars immediately? Is it possible? Will it be possible?
So there are different ways how to do that. As you said, I mean, you can do quantum communication with different quantum states, and this really depends on the use case, what you want to do and what you want to take. If you want to only do secure communication, quantum key distribution, then you don't need entanglement necessarily. You can also use it. So you have pros and cons in different cases. And also all those different technologies have different advantages and disadvantages. And the more complicated or fragile quantum states you use, for example, entanglement, the more careful you have to be about loss. Loss is decoherence that will destroy your quantum states, basically. So now if you talk about Mars missions, for example, then of course, if you talk about optical loss from Mars to Earth, this is really tremendous, right? So then one has to look into, okay, is this still doable? However, I might note one thing. When you mention Mars, there's also, of course, the topic of deep space communication. So now I'm not talking about connecting with quantum states and really doing quantum communication per se, but doing classical communication, but at the capacity limit. So if you're really starving in photons and you have nearly no signal left, this is also a line of active research. What is the best coding strategy? What is the best thing to do? And that also turns out to be that when you encode in the right way with photon number states and so on, you can actually be quite good and really reach the quantum limit of communicating with very, very long distance situations.
Any other question from the audience? It will be kind of the last one, so your last chance to ask a question. We have one here. You're taking the last chance. Well done.
Thank you. Hello, my name is William. I'm from University of Sherbrooke in Canada, and I'm asking you, in science of quantum technology, there is physician and there's also engineer to provide the technology where the scientists put them. So my question is, where are we going to see the first program or the first cohort of students of quantum engineer?
So as I understand, so that's a really concrete question. Where can you get a quantum space engineer, for example, right? That's a good question. So this is, of course, things that we propose to the governments as a proposal that would make sense. But I know that already now some institutions have started an engineering study with added quantum technology in some technical universities. So already now you can find some technical universities all over the world which start in that direction. Now, of course, if you want to go a step further and have quantum space engineer, that's even more specialized, right? So, but starting at least at the quantum engineering aspect, this is happening now, and we hope that this will become a bit more in the future.
In fact, if I can add something, as part of this quantum flagship from the European Commission, one of the pillars that the European Commission wanted to promote was, in fact, education. Because if we're going to be working on these topics, we need people that is well educated in these topics. So yeah, which is exciting.
And in the meantime, with the ongoing programs, we need to educate the engineers that we have there. And we start our first discussion on quantum key distribution and security with the 8 o'clock morning coffee in the cafeteria. So we are now in this learning process, and indeed that needs to go then into the education area as well.
Thanks. So actually for the last 6 minutes that we have, I would like to ask that all of you offer your recommendation to how we can move forward to see more quantum technologies in space. Both recommendation for the scientist community that we have here and a recommendation to the industry community that we also have here. So that now when we go back home, we all have an action to take recommended by you guys. I know it's tough, but let's take advantage of this, right?
So maybe I can start with a more general view from the scientific viewpoint. So I just would say to everyone, be a bit more brave. And that is, for the scientists, be more brave to interact with applied fields, with engineers, with industry. That is sometimes not easy because you really have to learn language and so on. But it is really useful and it helps a lot. For the politicians, maybe governments, be brave in putting in programs that maybe doesn't give you a big success within 3 years or so, and that also has a bit element of risk in it. So don't put too much effort into paper studies and paper studies and paper studies, because sometimes you have to do something, because otherwise you might lose track. Because I think in the future, of course, I mean, space is strategically very important for all the governments. And so if you don't do it, someone else will do it. So this is my message.
I have a simple message. Believe and trust in physics. It's based on natural laws, and they always win.
That certainly helps indeed. I think the challenge is not only with these two players, it's also with the agencies and governmental players. We need to have programs where actually industry and scientists come together and start to learn the right languages, because if that is not happening, it will not start from isolation, going out of the office in Christoph's area and enter into office in OHB. That usually doesn't happen. In this case, I know that OHB is quite successful on that. It has happened, but this is not natural. We need concrete programs where we work together on, coming from different fields, and being therefore a bit brave. And we tend, especially in my area, communication, satellite communication, we tend to think about the return of investment as a first question. So where is it used? We need to decouple a bit our programs on optical communication and especially on quantum technology a bit from this question, and be ready to go the extra mile. That is, I think, important. If we don't do it, others will do it. That's the point.
Okay, so as far as I understood, we need to be brave, believe in physics or trust in physics, and make sure the space agencies set up programs that can bring us all together to discuss these topics on the same table. So thank you very much for being today with us and sharing your insights and your expertise on this topic. And actually, before we say the final thank you and the applause to the experts here, I would like to also invite you all to join the next quantum technology session that is happening today as well, as a special session at 4:30. The title is QKD, the Future of Cryptography, so it's more focused on one of these applications we talked today here at the CCB Fokke Guelph-Saal. So if you're still interested to know more about this topic, 4:30, I invite you all to go there. Now, yes, a big round of applause for our experts here. Thank you very much.